This is the answer key for the Pre-Calc Unit 7 test review guide. And the first questions that I have on this review guide are just practice with factoring. And I'm actually going to work them out in the margin so that you can see the steps I'm following. So I'll start with 6x squared minus 5x plus 1. And when I look at this, remember that because there is a leading coefficient, I want to take that leading coefficient and multiply it by the constant term with signs and everything. They're both positive this time. So 6 times 1 is 6. And then what I want to do is think of 6 as a product or the answer to a multiplication problem, and negative 5 here, the coefficient on the middle term, as a sum or the addition to, or the answer to an addition problem. And I want two numbers that multiply to positive 6 and add up to negative 5. And those two numbers would be negative 2 and negative 3. And I'm going to just put x's with both of those. I'm going to take those two things and I'm going to replace the negative 5 with those two things. So now I've got 6x squared minus 2x minus 3x, and then bring down the plus 1. Now I'm going to factor this using grouping, and remember that grouping means that I'm looking at two terms at a time and taking out a GCF from each pair of terms. So a 2x comes out of the first two terms, and that leaves me with 3x and minus 1. And all I can take out of negative 3x plus 1 is 1, but remember that you also want to keep the same sign that you have in the middle there. And so this is going to be minus 1, and that gives you 3x minus 1 again. And if you've done this correctly, what you have in parentheses should be exactly the same for both of them. And so now my answer is going to be 2x minus 1 times 3x minus 1. So 2x minus 1 times 3x minus 1. The second problem here, let me switch colors, is 6x cubed minus 22x squared plus 12x. And you should see right off the bat that there is a 2 that can divide out from each term and an x that can divide out from each term. So your GCF is 2x, and that leaves me here with 3x squared minus 11x plus 6. And again, I'm thinking positive 3 times positive 6 is 18, and then 18 is a product, and negative 11 is a sum, and the two numbers that multiply to positive 18 and add up to negative 11 are negative 2 and negative 9. I'm going to put x's with those and then replace the negative 11x with that. And so now I've got, keep the 2x, don't get rid of the 2x, 3x squared minus 2x minus 9x plus 6, just bring the 6 down unchanged. And then you're going to take the GCF out of two terms at a time. And so that's going to be just an x in those first two. So I end up with 3x minus 2. And then always keep the sign of the middle term when you're doing the GCF here on the second pair of terms. And so that's going to be minus 3. And that's going to be 3x. And then minus 2, and again you've got the same thing exactly inside of both sets of parentheses. Keep the 2x in your answer, and then x minus 3, that's the GCFs, and the 3x minus 2. And so your answer for number 2 is going to be 2x quantity x minus 3 times quantity 3x minus 2. And then in letter C, when you see 4 terms, you know that you're going to do grouping. But I also see that I've got a GCF. And I think I have space to work this out right here. So I'm going to take out the 3 that is the GCF right off the bat, 3. That leaves me with x cubed minus 2x squared plus 5x and minus 10. And then remember that you have to keep that 3. And my first pair of terms that I'm looking at, the GCF, is x cubed minus 2x squared. So my GCF is x squared, and that leaves me with x minus 2. And then in my second pair of terms, there's a 5 that goes into both of those, and that also leaves me with x minus 2. And so my final answer here is 3 times x squared plus 5 times x minus 2. So number 2 just asks you to divide using synthetic division, but it also asks you to write your quotient as a polynomial. So your answer is going to be a polynomial. Be real careful to look at the directions for the different problems, because the process may be similar, and then when you get to the end of the problem, you have to write the answer differently. So in this first one, remember that if the divisor is given to you as a factor, like x plus 6, not x equals something, but as a linear factor, then that's the same as saying x equals negative 6, and that's when you change the sign. That's a 6. And so here, my coefficients are 1 for negative 5 and 42, and there's no quote-unquote missing coefficient. You've got x cubed, x squared, x to the first, and no x in the terms successively. So you don't need any 0 placeholders. So my coefficients are 1 for negative 5 and positive 42, and I'm dividing here by negative 6. Bring down the 1. 1 times negative 6 is negative 6. Add 4 plus negative 6 is negative 2. Multiply negative 2 times negative 6 is positive 12. Negative 5 plus 12 is positive 7. Negative 6 times positive 7 is negative 42. And your last number is a remainder. And I always put a box around my remainder to remind me that that's not part of the polynomial that has an x with an exponent on it. But these are the coefficients of the polynomial, and then this is my remainder. Now, also remember that if you start by dividing into a third degree polynomial, then the degree of your answer or your quotient is going to be second degree. So it's always 1 degree less because you divided out a whole degree. And so my answer is going to be 1x squared minus 2x plus 7. And because the remainder is 0, I don't need to write anything else, just x squared minus 2x plus 7. And then in letter B, notice that there's no x squared term, and so you're going to need to remember to use a 0 to stand in for the x squared coefficient. And also remember that you're dividing by negative 1 here. And so my coefficients are 4, 0, negative 3, negative 2, and you're dividing by negative 1. Bring down the 4. 4 times negative 1 is negative 4. 0 plus negative 4 is negative 4. Negative 4 times negative 1 is positive 4. Negative 3 plus 4 is positive 1. 1 times negative 1 is negative 1. And this time you have a remainder, and it's negative 3. So again, I started with a third degree, and so my quotient in my answer is going to be second degree, subtract 1 from the degree. But this time I have a remainder, and so I'm going to use negative 4 and 1. So 4x squared minus 4x plus 1, and then minus, because of the negative with the 3 over, and then go back up to your original divisor, 3 over x plus 1, and that's how you write a remainder when you're dividing polynomials. Let me just make sure that it's obvious which problem is which. All right. Now, you can also use synthetic division to test if a binomial is a factor of a given polynomial. And so, for example, here, I can divide by, and again, it's dividing by -2 here. I can divide using synthetic division here, and if the remainder is 0, then I would say, yes, this is a factor, or if it's not 0, then I say, no, this is not a factor. So my coefficients are 2, -3, -5, and you do want to use a 0 for that missing constant term, and I'm dividing by the -2. So to bring down the first 2 times -2 is -4, -3 and -4 is -7, -7 times -2 is +14, -5 plus 14 is 9, 9 times -2 is -18, and since your remainder here is not 0, you're going to actually say, no, x plus 2 is not a factor. If you want to write a complete sentence of f of x. The other example here, I'm dividing by x equals +1, and my coefficient, I'm not missing, quote unquote, missing any terms, so I'm just going to write the coefficients 1, -4, +9, -6. Dividing by 1, and so bring down the 1, 1 times 1 is 1, -4 and 1 is -3, -3 times 1 is -3, 9 plus -3 is +6, +6 times 1 is 6, and -6 plus 6 is 0. When your remainder is 0, then you say yes, x minus 1 is a factor, and it would be super accurate to then write it as a multiplication problem. And I'm getting the x squared minus 3x plus 6 from the quotient row of the synthetic division. Now, for number 4, we like to call using the use of synthetic division for evaluating a function, we like to call that synthetic substitution. It's still just synthetic division, and you're, again, dividing by this number. Don't change the sign this time, because you're dividing by exactly x equals 4. Notice that you're missing an x term, so you're going to need to use a 0 here. And so my coefficients are -1, +8, 0x, and 63. And I'm dividing by 4. Bring down the -1. -1 times 4 is -4. 8 plus -4 is 4. 4 times 4 is 16. 0 plus 16 is 16. 16 times 4, pause, calculator, is 64, and 63 plus 64 is 127. Now, you're not done. Make sure that when you write your answer that you put it in function notation. F of 4, remember that's the number that you divided by up here, f of 4 is equal to 127, and that's really how you want to write your answer to the synthetic substitution problems. So another synthetic substitution problem here. It's a little bigger, and you're missing a couple terms. X to the 5th, x to the 4th, you'll have a 0. X to the 3rd, x to the 2nd, and x to the 1st, you'll also have a 0. So Your coefficients are 2, 0, -10, -19, 0, and -45. And I'm dividing by 3. Ooh. So bring down the 2. 2 times 3 is 6. 0 plus 6 is 6. 6 times 3 is 18. -10 plus 18 is 8. 8 times 3 is 24. -19 plus 24 is 5. 5 times 3 is 15. 0 plus 15 is 15. 15 times 3 is 45. And again, you want to write your answer to this, -45 and 45 is 0. And you want to write your answer to this as in function notation. So here you have f of 3 is equal to 0, just like that. And I kind of hiccuped in the middle of doing that problem because the power in my house all went out. And so I sat in here in the dark doing synthetic division on my iPad. And you really don't care about the power in my house. So anyway, if it says given that something is a factor, what you really need to remember is that when you do this division, when you divide the polynomial by x equals 2, you will get 0. Because I'm telling you that it's a factor, and it's a factor if the remainder is 0. So you want to divide so that you can get the quotient, and the quotient will be something that you can then factor. So here I go. I'm gonna use 6, -13, 1, and +2, and I'm dividing by 2. Bring down the 6. 6 times 2 is 12. -13 plus 12 is -1. -1 times 2 is -2. 1 plus -2 is -1. -1 times 2 is -2. That's what you wanted, so that you have that 0 there. And the quotient is 6x squared minus 1x minus 1, and you want to factor that. So here, I'm going to factor that right here. 6x squared minus 1x minus 1, and 6 times -1 is -6, and so I want two numbers that multiply to -6 and add up to this -1 here, and that would be -3 and +2, and so I'm going to replace that term, the -x, with -3x plus 2x. So 6x squared minus 3x plus 2x minus 1. And then I'm going to do a GCF, so I've got 3x times 2x minus 1 plus 1 times 2x minus 1. Be careful when you're grouping that if your GCF is 1 or -1, you still want to write it because that's part of your answer. And sometimes when students forget to write it, they forget to write the 1 as part of their answer. So now I have 3x plus 1 times 2x minus 1. But the directions say to write f of x, so I want to write what's equal to f of x as a product. So I want to take those two linear factors and what I divided by, and my answer is all of those things multiplied. So my answer is going to be that 3x plus 1 times 2x minus 1 times the x minus 2 that I divided by at the very beginning, and that's my product of factors, meaning I've got a factor times a factor times a factor. That's my product of factors that are all equal to the original f of x. So let's do another problem like that. Here I have a function, and I'm given that x plus 1 is a factor, so I'll be dividing by x equals -1. Let me see if I can squeeze my synthetic division into this little space here. 8, -5, negative 19 and negative 6, and I'm dividing by negative 1. Bring down the 8. 8 times negative 1 is negative 8. Negative 5 and negative 8 is negative 13. Negative 13 times negative 1 is positive 13. Negative 19 and positive 13 is negative 6. Negative 6 times negative 1 is positive 6, and negative 6 and positive 6 are 0, which is what you were expecting. And so the function that you're going to factor, or the quadratic that you're going to factor, is 8x squared minus 13x minus 6. And so I'm going to factor that way over here. So I've got 8x squared minus 13x minus 6. And 18 times 6, 8 times negative 6 is going to be negative 48. And I need two numbers that multiply to negative 48 and add up to negative 13, and that's going to be negative 16 and positive 3. And I'm going to put x's with both of those, and I'm going to replace this term with the negative 16x and the 3x. So 8x squared minus 16x plus 3x minus 6. And I'm going to factor 8x out of the first two terms, so I'm left with x minus 2, and plus 3 out of the next two terms, and I'm again left with x minus 2. And so here I have 8x plus 3 times x minus 2, and then I'm going to come back and bring down my x plus 1 that was from my original division. And so again, what I'm saying here is that this polynomial, 8x cubed minus 5x squared minus 19x minus 6, is equal to this product of factors. If you were to multiply them all out, that's the answer that you would get. And here at the bottom of the page, you have a problem that's asking you to do several different things. So the first thing that you're asked to do is to list all possible rational zeros. So that's that theorem where you look at P and you look at Q and you think of all the factors of P and Q. So your positive 12 is P, and your positive 2 is Q. And remember, I shouldn't have said positive because you don't really need to worry about positive or negative with P and Q, because you're going to assume all positive and negative factors. Remember that it's P over Q, and so you want to list the factors of 12 in the numerator, so it'll be plus or minus 12, plus or minus 6, plus or minus 4, plus or minus 3, plus or minus 2, plus or minus 1, all over plus or minus 2 and plus or minus 1. And you want to look at every possible combination of 12 over 2, 6 over 2, 4 over 2, 3 over 2, 2 over 2, 1 over 2, and then 12 over 1, 6 over 1, 4 over 1, 3 over 1, 2 over 1, 1 over 1. I actually want you to write all those out. And so I'll start with the ones because those are the easier denominators. So 12 over 1, 6 over 1, 4 over 1, and so on. So I get plus or minus 12, plus or minus 6, plus or minus 4, plus or minus 3, plus or minus 2, plus or minus 1. And then take each of those over 2. But for example, when you're doing 6 over 2, well, 6 over 2 is 3, and you've already got 3. So you don't need to write that again. Excuse me. 12 over 2 is 6. 6 over 2 is 3. I've already got both of those. 4 over 2 is 2. I've got that. But I don't have 3 over 2. So plus or minus 3 over 2. 2 over 2 is 1, so I've already got that. And then 1 over 2, which I don't have, so plus or minus 1 over 2. So your list of possible rational zeros is all of those numbers. And although that's 16 numbers, you should be able to fairly quickly determine if those are rational functions by looking at the graph. And by all means, look at the graph. Go back and graph the original function. Go back up to this. Slap that into Desmos and just figure out which of these is rational zero. Technically, I should make you go to the table on the graphing calculator and go through the table and look for where the y values are zero. Remember, that doesn't get you fraction zeros, fraction x values that are roots or zeros. And for the sake of taking a test, remember you want the right answer, and I don't care if you use Desmos or the calculator to get there, but use what's going to take the least amount of time. This is number 6 from the Pre-Calc Unit 7 test review guide. Now, we've already listed all of the possible rational roots, and you can go into, as we did in class, you can go into your TI-84, type the equation, and then hit second graph, and it'll give you a table of x and y values, and look for where the y values are zero. Remember that will not give you the fraction possible rational roots, the positive and negative 3/2 and positive and negative 1/2. Really, it's sufficient at this point for you to go ahead and in Desmos and just type the equation. So that's 2x to the 4th plus 7x cubed minus 6x squared minus 23x plus 12. And just look, now you know that this is a 4th degree equation, and so you're just going to look at the 4 x-intercepts, and you can see that for sure negative 3 is a rational root. I would say that 2.562, that's not rational, whereas 0.5, that's your 1/2, so that's a rational root, and then this 1.562, again, that's also not rational. So these two values are irrational, but we're going to list the negative 3 and the 1/2, the positive 1/2, as two of the rational roots, and go and divide by those to solve for the other two roots. Now, when you look at the graph, you see that the rational zeros, I'm going to change colors here. So we have determined that the actual rational zeros, or the rational roots, are positive 1/2 and negative 3, because the graph has x-intercepts at those two rational numbers. But you also see, when you look at the graph of this, it has negative 3 and 1, and please don't write 0.5, but it has negative 3 and 1/2 as rational zeros, but it's also got two irrational x-intercepts, and you can tell that when you click on the graph that you see a decimal answer that doesn't repeat or terminate. And so what you're going to want to do is divide by both the positive 1/2 and the negative 3. And when you do that, remember that because you started up here with a 4th degree polynomial, you divide by a number, it becomes 3rd degree. You divide the answer by another number, and it becomes 2nd degree. You'll get a quadratic equation that can either be factored or solved using the quadratic formula. Maybe I'm thinking about singing in this video. So let's divide by I'll divide by the negative 3 first. So my coefficients of my original function are 2, 7, negative 6, negative 23, and positive 12. And I'm dividing by negative 3, Bring down the 2. 2 times negative 3 is negative 6. 7, negative 6 is 1. 1 times negative 3 is negative 3. Negative 6 and negative 3 is negative 9. Negative 9 times negative 3 is positive 27. Negative 23 and positive 27 is positive 4. Positive 4 times negative 3 is negative 12. Because you know for a fact that these are x-intercepts, you know for a fact that your remainder here is going to be 0. What you really want is this quotient, because that's what you're going to divide the 1/2 by. So I'm going to take the 2, 1, negative 9, and 4. You can build that like a pyramid. You don't have to rewrite it if you don't want to. But now I'm dividing by 1/2. 2 times 1/2 is 1. 1 plus 1 is 2. 2 times 1/2 is 1. Negative 9 plus 1 is negative 8. Negative 8 times 1/2 is negative 4. 4 and negative 4 is 0. Again, you're expecting it to be 0 because you know that 1/2 is also a factor or an x-intercept of this solution or this function, and so you'll get 0 as a solution if you substitute 1/2. But what I'm really looking for here is this quadratic, 2x squared plus 2x minus 8. So what I'm going to do is take 2x squared plus 2x minus 8 and see if it's factorable. X squared plus x minus 4. This is definitely not how I wrote it out when I did the problem earlier, but I should get the same answer still. There's no two numbers that multiply to negative 4 and add up to positive 1, so it's not factorable, so I'm going to need to use the quadratic formula. And so remember that you want to look at the coefficients on each of the terms, and so a equals 1, b equals 1, and c equals negative 4. Here comes, fast forward if you don't want to hear. The quadratic formula is negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, you can come back now. So I'm going to take those three numbers and substitute them in. So x equals negative 1 plus or minus radical 1 squared minus 4 times 1 times negative 4 all over 2 times 1. And the next thing that I would simplify here is just what's inside of the radical. And so just go ahead and type that into your calculator as is, and you should get 17. So now you've got negative 1 plus or minus radical 17 all over 2. And the problem is asking, I worked way down there, didn't I? The problem is asking you to find all remaining zeros of f of x and no decimal answers. And what I like to do, just to make sure that I see all 4 of the solutions in the same place, is I like to write x equals positive 1/2, negative 3, and it was negative 1, right? Negative 1 plus or minus radical 17 over 2. Or if you really wanted to be picky, you could say x equals 1/2, negative 3, and negative 1/2 plus or minus 1/2 radical 17. And either one of those answers is acceptable. So number 7 has the same directions as number 6. And you want to start by listing all possible rational zeros of the function. And so in this case, p is 2 and q is 6. And remember that you want to write your rational zero possibilities with p over q. So I'm going to list positive and negative 2, positive and negative 1, over positive and negative 6, positive and negative 3, positive negative 2, positive negative 1. And so my possibilities, 2 over 6 is 1/3. 2 over 3, forget the plus or minus. 2 over 2 is 1, and 2 over 1 is 2, and then plus or minus 1 over 6. I already have 1 over 3, plus or minus 1 over 2, and then 1 over 1, I already have 1 over 1. So these are your all possible rational zeros, but then you want to look at the graph of the function to decide which ones are actually rational. And when you graph that function, I'll pause for a second so you can graph it. This is number 7 on your test review guide for Unit 7. And again, we've already done a list of all the possible roots, and that positive negative 1/3, positive negative 2/3, 1, 2, 1/6, and 1/2. So I'm going to go ahead and type the equation into Desmos. And again, it's a fourth degree equation, and I can see all 4 x-intercepts, which means that they're real, they're not imaginary. And when I look here, negative 2 is rational, this is negative 1/2, that's rational, this is positive 1/3, that's rational, and this is positive 1. Therefore, all 4 x-intercepts are rational. We know that there are no imaginary roots because the degree of the polynomial is 4, and there can only be 4 roots. And so all 4 roots are rational roots. And when you've graphed that function, you see that you have 4 x-intercepts, and those x-intercepts are x equals negative 2, and then negative 0.5 is negative 1/2, and then 0.333, which is positive 1/3, and positive 1. And because it's a 4th degree function or 4th degree polynomial, and you found 4 x-intercepts and they're all rational, that means that there are no other roots. So number 8 is kind of like the problem on the synthetic division homework. I think that was homework number 1. It was the last problem where you're looking to find a number. Constant is just a number to replace the c there that's going to divide evenly, or make x plus 2 divide evenly into that polynomial in the top, and that means that you're going to have a remainder of 0. So just start your synthetic division by writing c in the quotient row so that you don't have to worry about what the number is yet. So, and notice that you need to have a couple of zeros in there. So 1x to the 5th, 0x to the 4th, 0x to the 3rd, and then minus 2x to the 2nd, plus 1x. And then I'm going to use c as the constant term. And I'm dividing by negative 2. Remember that it's negative 2 because you want to think of what that would be as a solution. I'm divided by negative 2. Bring down the 1. 1 times negative 2 is negative 2. 0 negative 2 is negative 2. Negative 2 times negative 2 is positive 4. 0 plus 4 is 4. 4 times negative 2 is negative 8. Negative 2 and negative 8 is negative 10. Negative 10 times negative 2 is positive 20. 1 plus 20 is 21. 21 times negative 2 is negative 42. And this is where you want to really look closely. What should C be to make your final outcome 0? Well, you want C to be equal to positive 42. So your answer here is positive 42. Now, for number 9, I would say try to do this. I'm not going to put a problem like this on the test, obviously, where it's matching and I give you equations and graphs and have you match them, because you could just type them into your calculator. You would want to type them into your calculator to compare the graphs. But I want you to kind of test yourself and see if you can figure out based on the end behaviors and what you know about end behaviors, which of these graphs matches with which function equation. So for example, I see that all of the functions have odd end behavior, and all of the equations have odd degree. So that's not going to help me. But I see that on the right side of the graphs, 2 are up and let's get a different color here, 2 are down. So if the leading coefficient is positive, then it's going up. And if the leading coefficient is negative, then it's going down. So 2 and 4 are either B or D, and 1 and 3 are either A or C. And the next thing that I can look at is the number of turning points. And so if you see here, letter A has 1, 2, 3, 4 turning points. Letter B has 2 turning points. Letter C has 2 turning points. And letter D has kind of 1, 2, 3, 4 turning points, kind of. It has more than 2, that's for sure, because of that little doohickey in there. So B and C should be obvious to you that they're third degree functions. And so 1 is C and 2 is B. And it should be also obvious to you that A and D are fifth degree functions. And so I can decide that 3 is A and 4 is D. And again, you should be able to do that without going to the effort of typing all of those equations into your calculator just to look at them. But again, I'm not going to give you a problem exactly like this with matching on the test. But you should maybe be prepared to write something like in words about how you would know. Number 10, all I want you to do is to be able to type in the function into Desmos, type the function into Desmos or your graphing calculator, although Desmos probably is a little bit faster, and click on the points that are turning points and just write the turning points with 2 decimal place accuracy. So I will stop talking for a moment, pause the video, practice typing things into Desmos and clicking on the turning points. And when you come back, the answers will be here. I'll do number 10, both A and B in the same little Desmos clip. So you'll need to go ahead and just kind of look ahead at the two equations, and then you can go back to I'll go back to the other part of the video and actually write them into the answer key. So all you want to do here is type in the equation. So I'm looking at letter A. And then the question asks for the turning points. So all you're going to do is the turning points. Ooh, I zoomed in and out really fast. Didn't mean to do that. There we go. That's what I was looking to do. The turning points are just your relative mins and maxes. And so for letter A, you see these values, and you just click on them. And then I'll graph the other one. And you know that you can turn off or on a view of the graph of different equations if one gets in the way of another, just by clicking on that circle off to the left. So here's letter B, x to the 4th minus 2x cubed minus 4x squared plus squared plus 2x plus 3. And so that's the purple one, and I'm going to need to zoom out a little bit. And I am going to turn off the green for a minute, and look at the purple and just click on 1, 2, 3 turning points. And again, all you need to do is write the values to 2 decimal places. This really is an exercise in, do you know how to put a graph into your calculator and find turning points? That's literally all I'm checking here. A is green and B is purple. Okay, so we're back and you have the answers here in front of you. And I kind of invaded the space from one problem into the other problem, so that's why I am drawing little bubbles around them so you can see which answers go with which equation. Hopefully that works for you. Now another problem that you want to be able to do is if I give you upper and lower bounds to test for a function to see if all the zeros fall in that interval. Use exactly those numbers. I know that when I've done that in class, some of you have then used different numbers, but I'm saying test this interval, so you actually want to test the -5 and the +7 here. So the upper and lower bounds tests are 2 slightly different tests, but they both involve dividing using synthetic division. So I'm going to start with the lower bounds test, and so I'm going to divide by -5. And my coefficients are 2, -9, -18, +71, -30. Oh, that's ugly. And right now the 2 times -5 is -10, -9, -10 is -19. Take your calculator and multiply. Don't write my answer down. -19 times -5 is +95. -18 plus 95 is 77. 77 times -5 is -385. 71 plus -385 is -314. -314 times 5 is 1,570. -30 plus 1,570 is 1,540. And what you should see happen here is that you have alternating positive, negative, positive, negative, positive. And so if your quotient row is alternating positives and negatives, then that means that your lower bound test is verified. You don't have to write verified, but I'm just doing that for completion. So now you have verified the lower bound. Now I'm going to do exactly the same thing, dividing the upper bound into the same numbers, the 2, -9, -18, 71, 30, -30. But in this case, I want my quotient row to all be positive. So I'm going to do another synthetic division. I'm going to divide this time by 7. So I've got 2, -9, -18, 71, and -30. And I'm dividing by 7. 2, 14, -9 and 14 is 5. 5 times 7 is 35. -18 plus 35 is 17. 17 times 7 is 119. Blech. 71 plus 119 is 190. 190 times 7 is 1,330. -30 plus 1,330 is 1,300. And again, now you see that all of the numbers in the quotient row are positive numbers, and therefore you have also now verified that your upper bound is +7. So number 12 is kind of like numbers 6 and 7, where you're being asked to find all of the zeros of the function, and you would start by looking for the rational zeros. And it tells you no decimal answers, which means that if you get something that's going to be an irrational number or an imaginary number, that you need to work out that using the quadratic formula. So I'm going to start with the rational roots, and there are very few possibilities. I've either got this is P and this is Q, plus or minus 1 over plus or minus 2 plus or minus 1, and so it could be plus or minus 1/2 or plus or minus 1, and that's it. Those are my only 4 possibilities. But when I look at the graph of this, I see that I have a double root. This is number 12 in your test review guide, and you're asked to find all the zeros of the function and no decimal answers, which means that if it's irrational or if it's imaginary, you're going to need to actually use the quadratic formula. Oh, I think I sang when I made that part of the answer key. Yeah, I did. So anyway, I would always graph something where the graph might help you analyze the whole problem, even if eventually you have to solve it algebraically. If you get into the habit of graphing these things that I'm asking you questions about, what you can do is compare your algebraic answer to what you're seeing on the graph, and in that way you can kind of double check yourself. So anyway, this equation is 2x to the 4th minus 5x squared minus 2x plus 1. And I zoomed it right off the screen. So here, you're asked to find all the zeros of the function, and so I have zeros at -1, at 0.293, and at 1.707. So chances are 0.293 and 1.707 are irrational numbers, and so you're going to need to use the quadratic formula to solve for those. But -1 is a rational root, and you know that it's a possible rational root from the rational root theorem. But the other thing that you know by looking at the graph here is that the fact that the graph kind of bounces off of the axis, or to be more mathematically analytical, both sides of the graph, or both sides of the function, are on the same side of the x-axis. So here's the root, and to the left of the root, the function is above the x-axis, and to the right of the root, the function is above the x-axis. And when both sides of a root are on the same side of the x-axis, then in that situation, you will find that that's a double root, which means, all that to say, -1 is a root twice. And so when you go back to the video of the answer key, you'll see that I divide by -1, get a quotient, and then take that quotient and divide it by -1 again, because it's 2 roots really here. And that double root is at -1. A double root means that it's a zero, or a root that happens twice. And so I'm actually going to divide by -1 twice. So I'm going to do my synthetic division to, there's no x cubed term, so I have to put a 0, -5, -2, 1, dividing by -1, bring down the 2 times -1 is -2, 0, -2 is -2, -2 times -1 is +2, -5 plus 2 is -3, -3 times -1 is +3, -2 plus 3 is +1, +1 times -1 is -1, and you knew that you would expect a 0 remainder, because you know that -1 is a solution. And now, because -1 is a double root, and you get that from looking at the graph, you're going to divide by -1 again. So I'm going to take this quotient and I'm going to divide by -1 again. And this time my quotient is 2x squared minus 4x plus 1. That is not factorable. If I multiply 2 times 1, the first coefficient times the constant term, there are no two numbers that multiply to +2 and add up to -4. That's not factorable. So I'm going to use the quadratic formula where, let's write that again. So 2x squared minus 4x plus 1, a equals 2, b equals -4, c equals 1. The quadratic formula is -b plus or minus the square root of b squared minus 4ac all over 2a. Sorry, I didn't warn you this time, so if you didn't pause the video or fast forward, you're stuck listening to me sing. So when you substitute into here, x equals -b, if b is already negative, then it becomes positive, because -b means take the opposite sign on b. So that's going to be +4 plus or minus radical, and then you've got -4 squared minus 4 times 2 times 1 all over 2 times 2. And again, I will tell you that I would start by simplifying what's inside the radical and just type that exactly as is. Don't type the radical, just the stuff inside the radical into your calculator. 16 minus 4 times 2 times 1, and you get 8. So x equals 4 plus or minus radical 8 over 4, which you have to simplify the 8 to 2 radical 2. And now you would want to simplify this, this solution. And I would start with 4 over 4 plus or minus 2 over 4 radical 2. And that gives you 1 plus or minus 1/2 radical 2, or radical 2 over 2 if you wanted to. And the directions say find all zeros, so you might want to pull that all together by saying, okay, x equals -1, -1, and 1 plus or minus 1/2 radical 2. Now, in number 13, I gave you about a bazillion times more space than you need to do this problem, because the y-intercept happens when, let's just write this, when x equals 0. So I'm going to take a 0, 0, 0, 0, 0. If all of these functions have a 0 multiplied by them, the y-intercept is just going to be that last term that doesn't have a 0. And so for this function in number 13, your y-intercept is y equals 53. And that's really all you have to write. I don't need to see any of the things that I wrote in green. Just y equals 53 is sufficient. Or you could write the point 0, 53. Now, number 14, what I would do is go ahead and graph the function first in Desmos, just so that you're looking at it while you're answering the questions. So go ahead and pause the video now, and if I am able to insert some Desmos videos into this video, it'll be a little disjoint because I'll have to do that later. But go ahead and graph it on Desmos. I'm going to pause a second. You'll probably see other stuff with Desmos, and I'll talk about Desmos, and then you can come back to the graph, and we'll talk through the answers to the questions. This is number 14 from your test review guide, and remember that when you are asked to draw a graph, it's always good to see it first, to see a graphing calculator or Desmos and how that graph is going to look using a graphing utility. The other thing that you want to remember is because you want to get a table of x and y values, you have to start by typing f of x. We hadn't been doing that on the previous problems in this video, but for this one, because I want you to go back and graph other points, you'll need those ordered pairs. And the way you can get those ordered pairs is by starting the equation with f of x. So I'll type in f of x and then equals x to the fourth minus 2x cubed minus 3x squared plus 8x minus 4. And let me put that in projector mode for you so you can see it a little bit better. And I have 1, 2, 3 zeros. Looks like they're rational. Looks like the one right here, x equals positive 1, is a double root. I've got a turning point here. I've got a turning point here. Those are both minima. This 1, 0 is not only a double root, but it's also a maximum. And then I've got my y-intercept at 0, -4. So you've got all those different values that you can use when you're answering the questions and put those points on the graph. And the other thing that you're going to need, and I won't be going back and forth within one problem from Desmos to the video, but the other thing that you're going to need is your table of values. So click in the space that's immediately below the equation that you've typed, and then go up here to the plus sign where it says add item. And when you click on that, you should get a number of different choices. You want the choice that says table, but remember that you have to change the y1 to f of x1. And if you just type x and then 1, the Desmos automatically assumes that you mean that it's a subscript, and so it drops it down. The other thing that might be helpful is that if you just start typing -5, enter, -4, enter, if you just keep hitting enter, then after you've established a pattern, Desmos will assume your x values continue in that same pattern. The other thing that you want to keep in mind is that I have given you a graph space that is designed for this particular graph. So if my graph space that I've given you on the paper or on the review guide or the test goes from x is -5 to x is +5, your graph won't be outside of that space. Now you might not need that whole space, but it'll at least be sufficient for you to put the graph inside of that space. And so here are your x and y values, so you can graph any of the points pretty much from -2, 0 to +2, 0. The rest of those points would be off of the space that I gave you. All right, so do you have that function graphed in Desmos? You're looking at it. To answer the question about end behavior, what you want to do, and really, folks, you should be able to answer all of these questions without looking at the graph, just by, well, maybe not this or these. But you should be able to get a good idea of what the graph could look like by answering these questions and looking at the equation. So it's a bonus that you have access to something that will electronically graph these for you. But let's take a look at the leading term is the whole term. I want the coefficient, which is 1 here, and the x and the exponent on it. So your leading term is 1 times x to the 4th, and the degree of that is the highest exponent, that 4. So the degree is 4, the degree is even. And the leading coefficient is the thing that I didn't write, which is the 1 right there. And so your leading coefficient is positive, positive 1. Even means that the ends are doing the same thing. And positive means that the right end is going up. Therefore, both ends go up. And I want you to actually write that out, both ends up. So your end behavior is both ends up. Now, a fourth degree equation can have at most maximum 3 turning points. It's always 1 less than the degree. And now is the first time that you would have to click over to Desmos and look at the graph on Desmos. And I do see 3 turning points. And at this place, you can write them out with just 1 decimal because really the goal is to graph everything. And so the ordered pairs that I see on my graph are negative 1.2, comma, negative 12.4, 1, comma, 0, and 1.7, comma, negative 0.5. And I'm going to take those 3 points and I'm going to graph them over here. So negative 1.2, and this is a little bit hard to do on the iPad, but negative 1.2 and negative 12.4. Let's try to put that right about there. And 1, comma, 0, that's not hard to do. And then 1.7 and negative a half. That should, I'm going to zoom in for that one. 1.7 negative a half would be about there. I'm actually going to make that 1 point just a little bit smaller because that's pretty ugly, that big. So there we go. All right. So those 3 points are my turning points. And then I'm going to go back and answer more questions over here. Based on the equation, the y-intercept is y equals negative 4. Please don't just write negative 4, but actually write y equals or write the ordered pair for it. The degree of the function is 4. And your rational roots are, and you don't have to use the theorem for this, just use the graph. So your rational roots are negative 2, positive 1, and positive 2. And notice that there's a bounce in the graph at positive 1, and so that's going to be a double root. And so in this case, you've got 1, 2, 3, 4. You've got 4 rational roots. Therefore, there shouldn't be any other roots, so we're going to go ahead and write none here. But yes, I still want you to test for the upper and lower bounds. So if my roots are negative 2, 1, and 2, negative 2, we've already got 1 and 2, then I would step out. And when I say step out, I mean you're going to go away from the outside of what you think the graph is twice. And the textbooks will tell you 1 time, but sometimes it doesn't work, and so then you have to go again. I just step out twice to start with. And so I'm going to test from negative 4 to positive 4. I'm going to use that interval to test for my lower bound and for my upper bound. And so I'll just write that. You don't have to write it. I just want to see the test written out. So negative 4 to positive 4. And there's not a whole lot of space to do this here, but I got massive margins that you don't. So I'm going to test for my lower bound down here. And I'm dividing the original function 1, negative 2, negative 3, positive 8, negative 4. And I'm checking for the lower bound at negative 4. Bring down the 1. 1 times negative 4 is negative 4. Negative 6 times negative 4 is positive 24. Plus negative 3 is positive 21. Positive 21 times negative 4 is negative 84. Am I going too fast for you? 8 plus negative 84 is negative 76 times negative 4 is positive 304. Hope you used your calculator and didn't just write what I wrote. Negative 4 plus positive 304 is 300. And remember that what you're looking for with the lower bound is that every other number is either positive, negative, positive, negative, positive. So my lower bound checks, and now I'm going to check the upper bound, and I'm going to do a whole new synthetic division with the same divisor. And this time I'm testing positive 4. Bring down the 1. Times 4 is 4. Negative 2 plus 4 is 2. 2 times 4 is 8. Negative 3 plus 8 is 5. 5 times 4 is 20. 20 plus 8 is 28. 28 times 4. Grab your calculators, ladies and gentlemen. You should get 112. And then negative 4 plus 112 is 108. And what you're looking for in this situation for the upper bound is that the entire quotient row is positive numbers, and therefore my upper bound checks. So there's my lower bound and upper bound check. So I know that all of my zeros happen between negative 4 and positive 4. Now, the last step of the graphing process that I have listed here is that you want to graph any additional points. So use that table that you can make in Desmos to graph any other points that would happen on the graph. My table has negative 4, x is negative 4, y is 300, which isn't helpful. Negative 380, again, not helpful. We've already graphed negative 2, 0. But I can graph negative 112. And that's going to be slightly to the right of the turning point here. And that's going to be kind of hard to see, but it would look a little bit like that. I'm a tiny bit off there, but you get the idea. 0, negative 4. Oops, I never graphed the y-intercept. So here's my y-intercept at 0, negative 4. Definitely not going to go back in the video and reshoot that whole thing like I sometimes do when I mess up. 1, 0, 2, 0, which I have graphed both of those. And then 3 is positive 20, and I haven't given you room to graph positive 20. And so then the next thing that you want to do is just kind of try to draw a nice smooth curve through all of those points, which is pretty tricky on my iPad, but I shall try. And hopefully your graph looks more or less like this. There's all those answers that you wanted. And then here's the entire page for you. Let's do one more graph before you get into the rational expressions. And so you want to pause the video for a second and go ahead and type this function here into Desmos and click around a little bit to see how it looks. If you zoom in too close, you're going to miss a good chunk of the graph because there's some twists and turns that you're not expecting. What I would suggest is to kind of size the graph in Desmos the way I have it sized. The way I have the graph space sized on the paper. I will give you a graph space that anticipates the graph that you need to draw, and so you can match the dimensions of the graph in Desmos to that. 15 on your test review guide. And again, I'm not going to go back and forth between the Desmos and the actual writing of the answers on the review guide. So just kind of set this up in your phone or in your computer, wherever you're using Desmos, and take a look at how I've laid it out, and then you can kind of have that sitting next to you as you're working on the paper. So here I'm going to again type f of x, and the purpose of typing f of x is because I'm going to eventually make a table of values, and I need the f of x to be at the top of the y values column. So I've got f of x equals x to the 6th power plus 5x to the 5th power minus x to the 4th power minus 21x to the 3rd power. The other thing that you can do if you don't like how the screen looks, because if I were to zoom in, that's not helpful. I can't see all the turning points and not have the graph be too skinny. Look at that's gonna make me batty. So if you click on this wrench over here for graph settings, I'm over on the right, what you can do is change the range of your x-axis and y-axis values to match what I've given you on the paper. So here, for example, on the paper, your graph goes from -5, your x values go from -5 to +5. And oh, look at already, that looks better. And then your y values go from -40 to +60. And so that'll be sufficient for you to work with this graph and be able to click on what you need. So you've got 1, 2, 3, 4 x-intercepts or zeros. Notice that this one right here, 0, 0, is a triple root. So that means that you've got 1, 2, 3, 4, 5, 6 zeros. So you've got 6 x-intercepts, including this one that's a triple root, and the degree of the function is 6, therefore there are no imaginary roots. 1, 2, 3, 4 of them are rational. -3 and 0 are rational. The 1.828 and the -3.828, those are irrational roots, and so those will be listed next to other roots. You also can click here on your turning points, minimum, maximum, minimum. The 0, 0 does not count as a min or a max because it's decreasing here and decreasing here. There's no place where the points on either side of 0 are either both higher or both lower. They're higher over here and lower over here. Now remember that what you want to do next is go to add item and choose table, and then change y sub 1 to f of x sub 1. And then I'll start typing my x values at -5, and then just hit enter a number of times if you don't want to type each separate x value in. So now I have all my points from -5, x is -5 to x is +5, and I see that I can graph from x is -4 all the way to x is +2. But the second we get beyond -4 to +2, our numbers are outrageously bigger. So it gets really big really fast. So now that you're back, hopefully you have all of that graph typed into Desmos and you can look at it while you're working on this. To determine the end behavior here, your leading term is x to the 6th power. The degree, which is 6, is an even number, and your leading coefficient, +1, is positive. And so once again, both ends of this graph go up, or up and up. Because it's 6th degree, you could have 5 turning points. But in this function, there are only 3 turning points. There's that little do-jiggy in the middle of the graph between -2 and 0 that, or -2 and, +2, where it kind of loop-de-loops, or I call it a twist high. And so we'll talk about that a little bit in the Desmos part of the video, but you really only have 3 ordered pairs in this function, or 3 turning points, in this function. So list the ordered pairs. I have -3.5, -37.5. That'll be fun to graph. -2.1, 56.6, even more fun to graph. And 1.4, -27.1. also a blast to graph. So go ahead and graph those 3 points right now. So I've got the negative 3.5 and that negative 37.5, which is pretty difficult to approximate on this screen. So I'm just going to put it there and hope that's close. And then negative 2.1, 56.6, so that's going to be way up here. So negative 2.1, I'm going to put that right about there. And then the positive 1.4 and negative 27, positive 1.4, negative 27, so right about there. So my 3 turning points are there. My y-intercept is going to be 0. And so I'm going to draw that right now. So y-intercept at 0. That also means that there's an x-intercept at 0. The degree of the function is 6, which means that I can have up to 6 x-intercepts. And my rational roots are at negative 3 and 0. But because the shape of the graph at 0 kind of goes like this, we're going to call that a triple root. So that counts 3 times because it looks like that. So I actually have 1, 2, 3, 4 roots already, and the other 2 roots have decimals. Because this is just for the purpose of drawing an accurate graph of this function, we're just going to list the decimal answers. I'm not going to ask you to divide or to factor anything when you're graphing. So my other roots, the irrational roots, are x equals negative 3.8 and positive 1.8. So I'm going to graph those points over here. Negative 3, 0. I've already graphed 0, 0. And now I want to graph negative 3.8, which is about here, and positive 1.8, which is about there. And now I am going to look at my upper and lower bounds, and I'm going to go past negative 4 to negative 5, and then out again to negative 6. So I'll test negative 6, and then here I'll go to 2 and then to 3, and you could go out to 4. I originally tested negative 5 and positive 3, and the negative 5 didn't work. So I did what I tell you guys not to do, and went out once, and it just didn't work. So negative 6 definitely works, and positive 3 definitely works. So I'm going to test those upper bounds. And that was why I hesitated a minute ago. I actually had to go back and delete part of the video. I'm going to do that over here. There are really some ugly numbers. You've got to put those 3 zeros at the end because you don't have an x squared term, an x term, or a number term. So when I test for my lower bound, I'm going to divide by that negative 6, and my coefficients are 1, 5, negative 1, negative 21, and then 0, 0, 0, and I'm totally going to run out of space here. Bring down the 1 times negative 6, negative 6. Zoom in so I lose less space. Negative 1 times negative 6 is positive 6. Negative 1 plus 6 is 5. 5 times negative 6 is negative 30. Negative 21 and negative 30 is negative 51. Negative 51 times negative 6 is positive 306. 0 plus 306, 306. Times negative 6 is negative 1,836. Negative 1,836 times negative 6 is 11,016. And your lower bound test here works just fine because you alternate between positive, negative, positive, negative, getting pretty big positive, getting super big negative, and getting ridiculous positive. I'm going to do my upper bound test. The numbers are also pretty big. So for the upper bound, this time I'm dividing by positive 3. Going to try to squeeze this in a little bit better here. 1, 5, negative 1, negative 21, 0, 0, 0. And we're bringing down the 1 times 3 is 3, 5 and 3 is 8. 8 times 3 is 24, negative 1, 24 is 23, times 3 is 69, negative 21 and 69 is 48. 48 times 3 is 144, 0 and 144. 144 times 3 is 432, and 432 times 3 is 1,296. And therefore, we have the whole bottom row is positive, and therefore this the function passes here, both the lower and the upper bounds test for the interval -6 to +3. That was painful. So now on your on Desmos, you've got a table of values. And I started at -4, and it goes all the way up to +64, which I can't graph. We know that we have a 0 at -3, so I've already got that point graphed. -2 has a point at 56, and so that's just a little bit to the right and below the maximum that you have, the relative maximum that you have there. And -116, I can also graph. -116 would be right about there. And then I've already got 0, 0 graphed. +1, -16, that's another one that I can graph without too much difficulty. +2, and then +40 is right about there. And the 3 and 4 go up into the thousands fairly quickly. And you can kind of start to see the shape of the graph here. So go ahead and draw yourself a nice, neat curve through all these points. I know that my end behavior on the left goes up. And then there's my maximum way up there. Ooh. And then there's that little do-jiggy in here where it kind of does a twist tie, and that's a minimum. And then that goes up to infinity on that side, and your graph kind of sort of looks like that, or I hope it should look sort of like that. So moving on to the rational functions, are we ready to factor? So let's do some factoring. I am going to factor the numerator here to be x plus 2 times x minus 2. Notice I'm saying x and writing a. That is a special teacher's superpower. And then when I factor the bottom, please, folks, pause the video. I am not going to walk you through any more factoring here. Factor that. Use grouping or the box method or whatever method you use, but make sure that you get the answer right. Come back and you should have 2a plus 1 times a minus 2, and your a minus 2's cancel, and your answer for this problem should be a plus 2 over 2a plus 1. In letter B, your numerator has a GCF of -8. Actually, you know what I'm going to do before I do that, just because it makes my eyes happier? I'm going to write that numerator in standard form. So -8x squared plus 16x. And that's just a little bit easier to think about and process. And so I am going to now factor out the GCF that's in the numerator. So that's a -8. negative 8x, and that leaves me with x minus 2 in the numerator. And I'm going to factor the denominator. That's going to be x minus 2 times x minus 2. And 1x minus 2 cancels with the 1x minus 2. And I end up with negative 8x over x minus 2. In letter C, it's a multiplication problem. And in letter C, I see that I have a GCF in one numerator and another GCF in one denominator. So I'm going to just factor out those GCFs. So I've got 4 times x plus 10 all over 3x times 9x over 3 times x plus 10. Now I'm going to cancel the x plus 10s, but I can also cancel this x here with the 9 and the x with the 3. I can also say 3 times 3 is 9, or you can cancel each 3 separately. But at the end of the problem, all you have left is that 4, and it's in the numerator, so it's just 4. Don't write 4 over 1. In letter D, I have to factor all 4 of those things. Why don't you pause the video, factor them, and come back when you're done. So you should have w minus 3 times w minus 8 over w minus 10 times w minus 8. In the second fraction, you should have w minus 5 over w minus 10 all over w minus 4 over w minus 5. I can cancel when it's multiplying, and this really is only when it's a multiplication problem. I can cancel from any numerator to any denominator. So for example, I've got that w minus 10 at the far ends, but I can still cancel them. I've got the w minus 8 here, I've got the w minus 5 here, and so my final answer is just the w minus 3 in the numerator and w minus 4 in the denominator. Now, for letter E, remember that I said that you can, when you're dividing, you have to flip the second fraction over. You can either do that first, or you can factor everything first, or if you're super good at this, you can flip and factor all in the same step, but you have to do both things before you start canceling anything. So at some point, I want to see that you have written out here x times x plus 7 over 3x times 3 times x minus 7 over 7 plus x times 7 minus x. Now, first of all, make sure you see up here that because the 49 is first, down here the 7's have to be first. And because the x is second, the x's have to be after the plus and minus signs there. Now, you have both factored and flipped, and now you can start canceling things. And I have an x and I have a 3, so I'm going to cancel both the x and the 3. I have an x plus 7 and 7 plus x. Those are the same thing. And here I have x minus 7 and 7 minus x. And remember that when you have a subtraction in a numerator that's one direction and that's exactly opposite in the denominator, when you cancel those, it leaves a negative 1. And at this point, that's the only thing that you're left with, and so that whole problem just equals negative 1. In letter F, you've also got a division problem, and like I said, pause the video, factor and flip, or flip and factor, but do both of those things before you come back. right, so check your factoring. Make sure that you have both factored and flipped it, and now you can start canceling factors. And I see an x plus 3 here and an x plus 3 here. And then I see this 3 minus 2x and 2x minus 3. And when I cancel those, remember that leaves me with a negative 1. Now, be real careful when you do these problems because it's easy to lose something. So I've got the 3 plus 2x over x plus 3. I've got the 2x minus 1. I've got the 4, and I've got the negative 1. That's a whole lot of stuff. Don't forget to write anything. So in my answer, I have 3 plus 2x times 2x minus 1. That's all in a numerator. Now, you can put the negative 1 in the numerator or in the denominator. I like to put it if I have a whole number, so I put it with a 4. You don't have to do it my way. Negative 4 parentheses x plus 3, and I just check and make sure that I found everything that didn't cancel, and that's going to be my answer for letter F. Okay, are we ready to add and subtract some fractions? Woohoo! So remember that when you're adding and subtracting, you want to have common denominators. And the first thing that you're going to want to do when you look at your denominators is decide if anything needs to be factored. So this denominator here, I can rewrite as x minus 2 times x minus 1. This whole denominator is x2 minus times x minus 2 times x minus 1. And I know that I could make both of these other denominators the same if I multiply. And so I'm going to write off to the side here that my least common denominator is just that, x minus 2 times x minus 1. And in order to make that first fraction, I'm going to multiply the top and the bottom by x minus 2. And to make that second fraction, I'm going to multiply both the top and the bottom by x minus 1. And then I'm going to make my whole big new numerator, this whole big ugly addition problem up here. Yuck, 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 yuck. Don't leave anything out because you have to include each of those things. And so from the first fraction, I've got x plus 1 times x minus 2. From the second fraction, I've got x plus 2 times x minus 1. And then from the third fraction, just plus 2x. So that's my whole big numerator. And now my LCD is my common denominator here, and that's just going to be my one itty-bitty denominator. Now, here's where you're going to love this problem. You have to FOIL twice this and this separately before you can start combining and simplifying like terms. You can't cancel yet. There's nothing here to cancel yet. So when I FOIL the stuff that I highlighted in green, I get x squared minus 1x and then minus 2. And when I FOIL the stuff that I wrote or highlighted in yellow, I get x squared plus 1x and minus 2, and then just bring down plus 2x. And I'm still going to keep all of that over my denominator, x minus 1 times x minus 2. And now I'm going to combine like terms. And when I do that, I get 2x squared plus 2x minus 4. I can factor that numerator, and I'm going to both, you're going to need to do this on the side of your paper, but I can take out a 2 as a GCF, and then I can also factor the quadratic that you have after you factor the GCF out. So what you end up with is in the numerator 2 times x plus 2 times x minus 1 all over, and then my common denominator, which is x minus 2 times x minus 1. Oh, and look, hey, I've got stuff that cancels, and so my final answer for this problem is 2 times x plus 2 in the numerator and x minus 2 in the denominator. And please help your elderly teacher by putting a box around or a circle around your final answer so that I can find it, because some of you don't necessarily work down step by step, but you kind of work all over the place, and I need to be able to find your answer. Let's take a look at letter H. H is a subtraction problem. The first thing that I'm going to do is factor this first denominator, and I get x plus 5 times x minus 6. And I see in the second denominator that in order to get my LCD, which is x plus 5 times x minus 6, I can just multiply the top and the bottom by x plus 5. Some kind of fancy x there. Okay. So now remember that your subtraction in the numerator is going to be 3x squared minus, and then this whole thing over here. So it gets ugly before it gets pretty. So I'm going to write all of that out. So I've got 3x squared minus, and then the quantity 3x plus 5 times x plus 5 all over my LCD, which is x plus 5 times x minus 6. Now, you have to keep the parentheses when you're foiling. So you're going to foil the thing with the both parentheses, but you have to keep that in parentheses because of the subtraction. So when I foil this, keep the 3x squared in the numerator and then the minus. When you FOIL that, you should get 3x squared plus 20x plus 25. Keep that in parentheses. Keep your same denominator, x plus 5 times x minus 6. And now when you simplify, remember that you have to multiply -1 times each of the terms in there. I think I can write that over here. And so what you end up with in the numerator is 3x squared minus 3x squared minus 20x and then minus 25 all over x plus 5 times x minus 6. What's pretty cool here now is that those 3x squared minus 3x squared is 0, so they cancel each other out, and so my final answer is -20x minus 25 all over x plus 5 times x minus 6. Now, if this bothers your eyes, because you could factor a -5 out of the numerator, you can factor a -5 out of the numerator, and that would be perfectly fine. But what I'm going to say is that if you can't cancel anything at the end of the problem, then I don't care if you factor that numerator or not, because neither -5 nor 4x plus 5 is going to cancel with anything in the denominator, so you're just done. Now let's look at these two complex fractions. Remember that a complex fraction is just a big obnoxious division problem, and it's going to be this big obnoxious numerator divided by this equally big obnoxious denominator. And so what I'm going to do is I'm going to write that out as a division problem. So I'm going to use big parentheses, and I'm going to say 16 minus 1 over x squared, and that whole thing divided by, and then the denominator, 1 over 4x squared minus 4. So rewrite that as a division problem to start with. But then you want to simplify each of these things separately, get an answer that's completely simplified, and then do your division at the very end. So I'm going to just start with the blue, and I want x squared to be my common denominator, so I'm going to multiply by x squared in both the top and the bottom, and I end up with 16x squared minus 1 all over x squared. And that's all it takes to simplify the blue. And now I'm going to simplify the green. And again, I'm going to put that 4 over 1. And I want the denominator to be 4x squared. So I'm going to multiply by 4x squared in the top and in the bottom. And my simplified fraction for the denominator is 1 minus 16x squared all over 4x squared. And then big division sign because I'm dividing the blue divided by the green. So the next thing that you want to do, and I'm actually going to skip the factoring step here because I see that I am going to be able to cancel without factoring the 16x squared minus 1. You could write 4x plus 1, 4x minus 1, and 1 plus 4x, 1 minus 4x. All of that stuff is going to cancel whether I factor or not. So let me rewrite this whole problem. Then with the flip, and I've got 16x squared minus 1 over x squared times that 4x squared over 1 minus 16x squared. And now the x squared here cancels with the x squared here. These, when you cancel them, leave a negative 1 because it's that subtraction written forward and backwards. And so I've got the 4 on the top and the negative 1 from the subtraction that I canceled. And so that whole entire fraction just equals negative 4. And for letter K, here, again, I'm going to look at this as one big division problem. And hang on a second. So I'm going to look at the numerator, or the thing that is part of the division problem there, 1 over x plus 1 plus 1/2. And then the big denominator is this big huge fraction, 3 over 2x squared plus 4x plus 2. And again, I'm going to write that out as a division problem. So I'm going to start with a big set of parentheses and write 1 over x plus 1 plus 1/2, big parentheses, divided by, and then that big denominator, that is one ugly denominator, 3 over 2x squared plus 4x plus 2, because I couldn't have given you a problem that didn't have so many little different moving parts, could I? So now you've rewritten that as a division problem. You want to take each one of those things separately. So I'm going to look at the 1 over x plus 1, and my common denominator here would have to be 2 times x plus 1. And what I end up with then in the blue is 2 plus x plus 1 over 2 times x plus 1. I know I can simplify that numerator by combining like terms, but this is where I am right now, so I'll do that in a minute. Let me switch over to the green the green part of the function though, and the first thing I'm going to do is factor the denominator. You should see that you have a GCF of 2. So take out the 2 and you have x squared plus 2x plus 1. Grab a scratch sheet of paper and factor that. And you should have 2 times x plus 1 times x plus 1. And so now that whole fraction is 3 over, and then that factored 2 times x plus 1 times x plus 1. So the green is 3 over 2 times x plus 1 times x plus 1. Now I'm going to flip the second, so I'm going to rewrite this whole thing, and I'm going to flip the second fraction. I'm also going to simplify this first numerator, combine the like terms there. So I've got here x plus 3 over 2 times x plus 1 times, and then flip 2 times x plus 1 times x plus 1 all over 3. And you should see that the 2 cancels with the 2, and the x plus 1 cancels with one of the x plus 1s. And what I have left are the x plus 3 here, the x plus 1 here, and the 3 here. And so my final answer to this is x plus 3 over x plus 1 all over 3. So let's move on to the equation solving. And remember that one of the ways that I showed you to solve equation is that if you have a fraction, not an addition problem with fractions, but a fraction on one side of the equation and a fraction on the other side of the equation, you can look at the cross products, because in a proportion, and this is really what we're looking at, is a proportion, the cross products should be equal. So I've got x minus 5 times x plus 3 is equal to negative 3 times 4. I'm going to simplify and FOIL and do all that stuff. So I've got x squared minus 2x minus 15 equals negative 12. I'm going to add 12 to both sides. So now I've got x squared minus 2x minus 3 equals 0. And then I want to factor that. X minus 3 times x plus 1 equals 0. And that gives me x equals 3 and x equals negative 1. And the thing that you want to do is go back to the original denominators and ask yourself if either of those answers could make a denominator 0. And the only number that could make either denominator 0 is x equals negative 3. And my solution is x equals positive 3. So both solutions are good. There's no extraneous solution. In letter B, we don't have just one fraction. Over here, we have 2 fractions being added. So I would use the what I describe as the method number 2 in your notes here, and I would go ahead and factor this last denominator, and I would look for a least common denominator. In this case, it's going to be x plus 2x minus 2. So I can multiply by x minus 2 over x minus 2, and I can multiply here by x plus 2 times x plus 2. Oops. And now all 3 fractions have a denominator of x plus 2 times x minus 2. Now this next step only works for equations. So if you're solving an equation, and if all of your denominators are the same, then all you need to solve is the equation that is made up by the numerators. And so I'm going to rewrite that whole thing as 7 times x minus 2 plus 5 times x plus 2 equals 10x minus 2. And now I'm going to solve that equation. I'll start by distributing here. 7x minus 14 plus 5x plus 10 equals 10x minus 2. And then I'm going to combine like terms, and I get 12x minus 4 equals 10x minus 2. And then I'm going to subtract 10x from both sides, so I have 2x minus 4 equals negative 2. And I'm going to add 4 to both sides, so I have 2x equals positive 2, and x equals 1. And before I decide that that's my final answer, I'll go up and look at these. And the only numbers that x can't equal positive or negative 2. And my answer is positive 1, so it's good. Good. Not extraneous. In letter C, I want to make sure that you see that the denominator of that first term is 1. So you've got x over 1. And this whole thing with the x minus 3 here and the 3 minus x there, well, that's kind of icky. So I am going to rewrite this as negative 1 times x minus 3. And so I'm going to need to multiply this times negative 1. And then in this first term over here, did I write negative 1 down there? No, I did not. Negative 1. And then in this term down here, I'm going to need to multiply by both negative 1 and x minus 3. So negative 1 and x minus 3 in both the numerator and denominator. And so now each of the terms, each of the denominators has the negative 1 and the x minus 3. And so now I'm going to just solve for the numerators. So I have negative 1 times x minus 3 minus 2 times negative 1 equals x minus 1. So I've got negative x squared plus 3x plus 2 equals x minus 1. Now, because I've got this negative x squared, I'm going to move all of my terms over to the right so that it will be positive, a positive leading coefficient, so that I have 0 equals positive x squared, and then minus 3x on both sides is going to be negative 2x, and minus 2 on both sides is going to be minus 3, x squared minus 2x minus 3. And then that gives me 0 equals x minus 3 times x plus 1. And so x equals 3 and x equals negative 1. And when I go up and look at my original equation, I see that x cannot equal positive 3. Oh, and look, I've got positive 3 as a solution, so I'm going to cross that out and tell you that that's extraneous. Remember that I want you to write that and then indicate that the negative 1 is your only good answer. And then for letter D, again, I'm going to factor. This has another situation where you're going to need to work with a negative 1 to make the denominators the same. I was feeling extra vicious, I guess, when I wrote this review guide. So x minus 4 times x plus 3. This, so my LCD here is going to be x minus 4 times x plus 3. And what I'm going to do for this term is multiply by -1 and times x plus 3, and that'll take, the -1 will take care of the subtraction that's backwards. So I also have to multiply this by -1 and x plus 3 in the numerator. And over here, I'm going to multiply by the x minus 4 and x minus 4. And see that the only place that you need to use the -1 then is here, because this is the only place where the denominator has 4 minus x and not x minus 4. Because it's x minus 4 here and x minus 4 here, you don't need to multiply by that extra -1. Now that you've got all the denominators the same, you're going to solve just the numerators here, that equation. And remember, only get rid of the denominators when you're solving an equation, not when you're just plain adding or subtracting. So I've got 2 times x minus 4 minus 3 times -1 times x plus 3 equals 2x minus 2. So 2x minus 8. Now look at this. Plus 3, that whole thing is positive 3, and I'm going to distribute it across the parentheses, so I end up with plus 3x and plus 9 equals 2x minus 2. Make sure you understand what I did with the minus 3 and the minus 1. The -1 just makes the subtraction into an addition. Now I'm going to combine like terms, so I've got 5x plus 1 equals 2x minus 2. Subtract 2x from both sides. Subtract 1 from both sides. X equals -1. And the only numbers x can't equal are positive 4 and -3. And so therefore x equals -1 is good. Now we have some questions about the graphical characteristics of a rational function. And we'll start out with the domain. And that one should be pretty easy. You guys did really well in Unit 6 with domains and restricted domains. And remember that for a rational function, the domain is only restricted by what would make the denominator equal to 0. And so if I were you, I would graph them if you have time real quick to just check yourself. But you can also find it algebraically fairly easily by saying, I know that the denominator cannot be equal to 0. And so in this case, 2 cannot be equal to x. And therefore, my domain is -infinity to 2, not including 2, and then 2 to positive infinity, all round parentheses. The same thing in the next one. I know that x squared minus 9 cannot be equal to 0. X plus 3, x minus 3, or you could just add 9 to both sides and take the square root. But here you see that x cannot be equal to plus or minus 3. And therefore, my domain is -infinity to -3, not including -3, -3 to positive 3, and then positive 3 to positive infinity. And then in letter C is unique, and if I have a chance, I'll add a video with a section to this video with Desmos. So this is number 18C. I figured that you could do A and B without much input from me. But for 18C, I kind of wanted to walk you through. The answer is a little bit unexpected. And you're asked to find the domain for these 3 problems. And so the first thing that I want to point out is that with Desmos, I can't really find a way to have a numerator and denominator and have the numerator have multiple terms without using parentheses. If you find a way to do that, please, please, please let me know. But in the meantime, go ahead and type parentheses 3x squared plus x minus 5, close your parentheses, and then when you hit the slash or divide, it automatically then gives you a denominator, and you can type your x squared plus 1 without parentheses. So your graph should look something like this, and you'll see that there's no, there's actually 2 points in there. There's no place where there's no x value. There's no vertical asymptotes here. And in fact, that's because this denominator cannot equal 0. Whatever number you square for x, this term is going to be positive, and then you're adding a positive number to that. So no negative number. It's because of the squared. Anytime you square any number, whether it's positive or negative, your result is positive. And so that means that this can never be 0. And just a quick note, even though you're not asked to graph this or comment more about the graph, I kind of want to point out that your y-intercept here is slightly off from the minimum, which is there. So just keep in mind things like that with these graphs, that they don't always behave the way you're expecting them to behave. Anyway, this is why the answer to this graph is all real numbers, or the domain of this graph is all real numbers. But I would want to see what number would make x squared plus 1 equal to 0. And what you'll see is that x squared cannot equal negative 1. Well, if you solve that, that's imaginary. And when we're looking at the domain, we're actually looking at the real domain, so we're not talking about anything that's imaginary, and therefore there's no number that would make x squared plus 1 equal to 0, only an imaginary number. There's no real number that would make x squared plus 1 equal to 0, and therefore my domain is going to be all real numbers. So double check that you understand that. Take a look at the graph of it. Now this next section is asking you to find both the x-intercepts and the y-intercepts for these functions. And so remember that for the x-intercepts, you want to take the numerator and set the numerator equal to 0. So you're going to do 4x equals 0, and so x equals 0. And so your x-intercept is x equals 0. And for the y-intercept, you want to make all the x's zeros. And what I do when I'm thinking about the y-intercept is I just kind of cover up each of the terms that has an x in it. And if you've covered up the numerator, just think about that as 0. And your y-intercept then is 0 over 1, which is just 0. So y equals 0. Hint, if the x-intercept is 0, the y-intercept is 0. For any function, whether it's polynomial, rational, quadratic, linear, logarithmic, whatever it is, if the x-intercept is 0, the y-intercept is also 0. It's number 19a, and you are asked to find the x and y-intercepts algebraically. And again, I'll tell you that although I'm asking you to find them algebraically, and although I'm asking you to show me all the steps of finding them algebraically, if I were you, I would still check them on Desmos or on a graphing calculator, just to be sure that what you're finding algebraically matches up with what you're doing graphically. And if you're not, go back and double check everything. So for letter A, you've got 4x in the numerator, and you don't need the parentheses because it's just one term, and then x squared minus 3x plus 1 in the denominator. That is a funky looking graph, isn't it? But remember that this question is only about the x and y intercepts. And because you know here that your horizontal asymptote is 0, right? Because the degree of the denominator is bigger than the degree of the numerator. So your horizontal asymptote is 0 here. Remember that horizontal asymptotes are only about the end behavior. So that means, what is this function doing as x goes to negative infinity, and what is the graph doing as x goes to positive infinity? With horizontal asymptotes, very different from vertical asymptotes. With horizontal asymptotes, it doesn't matter what's happening in the middle of the graph. In fact, the graph can cross the horizontal asymptote, and that's just fine. Graph can never cross a vertical asymptote, and you have vertical asymptotes here and here in this equation, but you don't have to worry about that with horizontal. Having said all of that, the question is just asking about your x and y intercepts. And if you can look at your whole x-axis, the graph is going to be above the x-axis on the right, and it's going to be below the x-axis on the left. And if you're not sure, you can just kind of like scoot out the point to both ends to just see what those numbers are doing. And on the right, they're always positive, and on the left, they're always negative. So this is going to be the only place that the graph crosses, either the x-axis or the y-axis. And so 0 is both your x-intercept and your y-intercept. But again, you need to show those to me algebraically. And I've shown you how to do that in the written part of the answer key video. In letter B, again, to find the x-intercept, you want to set the numerator equal to 0. So 3x minus 5 equals 0. 3x equals 5. So x equals 5 over 3. And for the y-intercept, I would just ignore the terms that have x's in them and just look at the two constant terms. So your y-intercept is going to be that negative 5 over positive 20. And so my y-intercept is going to equal negative 1/4. Simplify the fraction. And for letter C, be careful because there's a hole. And so you have to make sure that you're not thinking that the hole is an x-intercept. So here's what I mean. Start by factoring the numerator and denominator. So you get x minus 7 over x plus 3 and x minus 4 over x plus 3. And you cancel the x plus 3's. And what that means is that there's a hole at x equals negative 3. So if there's a hole there, it can't be an x-intercept because there's a point missing. That's like a point that's just not there. And so if that point happens on the x-axis, it can't be an x-intercept. So your only x-intercept here can be x equals 7. So your x-intercept, you're going to factor and cancel first and then set the numerator equal to 0. And so your x-intercept is only x equals 7. And then your y-intercept, I'm going to go back to the original function. And for the y-intercept, where did that line come from? Get rid of that. For the y-intercept, again, I'm going to ignore the terms that have the x's in them and just look at negative 21 over negative 12. So my y-intercept is going to be that negative 21 over negative 12. So y equals, and both of those are divisible by negative 3, and so I would get positive 7 over 4. So my y-intercept is 7/4. In C, take 2, I messed up the first take. You'll never see it. It's already been deleted. This is number 19C, and remember that if your numerator has multiple terms, you need to put parentheses just around the numerator. So we've got x squared minus 4x minus 21, and then over x squared minus x minus 12. And it may bother you that they both don't have parentheses, and it doesn't matter. Then you can go ahead and just put parentheses around the denominator if you want, but they're not necessary. Now, here's what you should have already done in the, and I show you this in the other part of the video, is that you would factor the numerator and the denominator, and you've already written that out. Hopefully you have in the numerator x minus 7 times x plus 3. And in the denominator you have x minus 4 times x plus 3. Both the numerator and denominator have an x plus 3, which means that cancels. And when you have a factor that cancels, that means that there's a hole in the graph. So x plus 3 is what cancels, and so x equals negative 3 is where your hole's going to be. And if you drag really slowly till you get on top of the, and it's kind of touch and go. You might not be able to find it easily, but if you drag carefully, you should be able to get to a place where, and I'm holding down on my mouse right now, you should be able to get to a place where you can see that at negative 3 your y value is undefined, and so that just means that there's a missing x and y value right there. And then the other thing that you could see is that the vertical asymptote of this graph is x equals 4 right there. By the way, if you ever wanted to actually look at an asymptote, I'm going off script here, you can just type the equation of the asymptote and then go over here and switch this to a dotted or a dashed line. I don't like that in projector mode. Let me change that to regular mode. And it looks kind of nice. I mean, you've got a nice looking asymptote there, and you can kind of see, that graph is going toward the vertical asymptote and not ever touching it. Now, the question actually asked about x and y intercepts. My apologies for getting off task here. So if you click here, you've got a y-intercept at 1.75, and in the on the paper we did negative 21 divided by negative 12. Both of those are divisible by 3, so that's going to be 7 over 4. Positive 7 over 4 because it's negative over negative. Positive 7 over 4 is positive 1.75. The x-intercept here is at 7, 0, and that's if you set the numerator equal to 0 after you've canceled. So you cancel out that x equals, or x plus 3, you cancel that out, and then your other factor in the numerator, x minus 7, that's your x-intercept. Now, you want to, for this problem, you want to find the holes and vertical asymptotes algebraically, which means Miss Applebacher needs to see the work that you've done for these problems, and you're not just taking it off of the graphing calculator and expecting full credit for that. So, holes only happen when a factor cancels. And any other value that would make the denominator 0 is a vertical asymptote. So in letter A, nothing cancels. So there's no hole. Anything that's not a hole but makes the denominator 0, like x equals 3, is a vertical asymptote. In letter B, you're going to need to factor first, So if I take out a GCF in the numerator, I get 4x plus 2 times 4x plus 1. In the denominator, I'm going to use my grouping or box method. Pause the video, factor that for yourself. You should get 4x plus 1 times x minus 2. Now you have something that factors, and so let's start with the whole. And the whole happens where 4x plus 1, the thing that factored, is equal to 0. 4x equals negative 1, and x equals negative 1/4. But I also want you to find the y value. So you find the y value of the whole by looking at what you didn't cancel. So I've got 2 over x minus 2. Substitute the x value of the whole into 2 over x minus 2. So I've got 2 over x minus 2, and I'm going to substitute the negative 1/4. So 2 over negative 1/4 minus 2, and all of that equals negative 8/9. So that's your y value of your whole. And so my whole is at negative 1/4, comma, negative 8/9. Whatever's not a whole then is going to be a vertical asymptote. Whatever makes the denominator 0 and isn't a whole is a vertical asymptote. And therefore, in this question, you've got a vertical asymptote at x equals positive 2, and that's from this. And then in this last one, remember that you have to factor first, and so I'm going to rewrite this as 2x over, the denominator has a GCF of x, and so it's going to be x times x minus 8 times x plus 3. Anything that cancels, like this x here, means that you have a whole. So I've got a whole at x equals 0, but I have to find the y value of the whole. To find the y value of the whole, I'm going to take the 2 and the x minus 8 times x plus 3, I don't like that 8, and substitute 0 for the x's. So 2 over 0 minus 8 times 0 plus 3. So that's 2 over negative 8 times 3. 2 over negative 24 is negative 1/12. And so my whole is at 0, comma, negative 1/12. And my vertical asymptotes are the other two things, the x minus 8 and the x plus 3. So my vertical asymptotes are at x equals positive 8 and x equals negative 3. Now I'm going to do number 20C, and do work on 20C, and then if you think you need to go back and adjust, I would say that that 20C might impact your thinking about letter B, 20B as well. I just didn't think that I needed to make videos for both of them, and I thought that C was more exemplary of some different things that I want to talk you through. So for letter C, 20C, I'm going to put 2x in the numerator and x cubed minus 5x squared minus 24x in the denominator. Now, first of all, you can see that you've got a GCF of x in the denominator and you have an x in the numerator. And so the x's should cancel, and we went through that in the other part of the video. That should mean that you've got a whole at x equals 0. And so I'm going to just kind of drag and see if there's a whole at x equals 0. And there is, so it's 0, comma, undefined. Do you see that if there's a hole at 0 for this graph, that you're not going to have a y-intercept? So if I gave you this question and I asked what are the y-intercepts, you would say there are none, or undefined, or NA, or whatever, because at the y-axis there is no x value. There is no y value, I'm sorry. So you don't have a y-intercept. The graph does not touch the y-axis technically. So your hole is there, and that's one of the things that you're asked to do. And in the other part of the video, I show you how to find the y value of that hole, and you'll get -1/12. Notice also that you've got a vertical asymptote here, and that's -3. You've got a vertical asymptote here, that's at +8. And again, kind of like I did in a couple of problems ago, if you wanted to check your asymptotes just to see if they look about right, you can type them in and then change them to a dashed line. I like to make my asymptotes red. And so you can see here that those asymptotes are accurately placed at +8 and -3. And then the horizontal asymptotes, and remember that there's different rules for all of these things, and you just have to remember the rules for them. The vertical asymptotes, or the horizontal asymptotes have to do with the degree of the numerator and the degree of the denominator. Remember that I won't give you any functions and ask about horizontal asymptotes if the degree of the numerator is higher and the degree of the denominator is lower. That would give you a slant asymptote, and we're not covering that in this course. So here, the degree of the numerator, the degree of the polynomial that's the numerator, is equal to 1. And here, the degree of the denominator is equal to 2. When the degree of the numerator is less and the degree of the denominator is greater, your horizontal asymptote is y equals 0. Okay, so here is number 21a, short and sweet, 3x over 5x squared plus 4. And you're asked to find the horizontal asymptote. Now, remember, we talked about this just a couple of minutes ago, but your horizontal asymptote, and this is different from the vertical asymptote, your horizontal asymptote is, hang on a second, let me just change these values and I'll go back to what I was saying. Your horizontal asymptote is only about the end behavior, and it's not about what happens in the middle of the graph. So I don't know why my mouse keeps connecting and disconnecting. I'm sorry that you're getting that in the video. I'm actually not even using a mouse. It's on the other side of the room in a bag. So for a horizontal asymptote only, it doesn't matter what's happening in the middle. It doesn't matter that the graph crosses it. The horizontal asymptote is only about the end behavior, and it has nothing to do with the middle of the graph. A vertical asymptote is completely different, and a vertical asymptote is the value that x cannot equal, and the graph cannot cross the path of a vertical asymptote. So here your horizontal asymptote is equal to 0 for part A. If the degree of the numerator and the degree of the denominator are the same, so here the degree of the numerator is 1, here the degree of the denominator is also 1, you have to write the numerator and denominator in standard form, and then your horizontal asymptote is the ratio or the fraction that's made by the two leading coefficients. And so your horizontal asymptote is y equals -3/4. Do 21b with you, and again I need to put parentheses around the numerator, and my graph looks like this, and I'm going to click on home because it will put me back to the original zoom that I had. And I think that in the other part of the video I rewrote the denominator here in standard form so that it was negative 4x plus 6, and that we said algebraically that the horizontal asymptote is the ratio of the two leading coefficients, because the degree of the numerator and the degree of the denominator are the same. You take the coefficient from 3x and the coefficient from negative 4x, so 3 over negative 4, and that's going to be your horizontal asymptote. And if you're not sure, type the equation of the horizontal asymptote, and because it's horizontal, you start with y equals, and then I'm going to make the fraction negative 3/4, and again I'm going to change this to a dashed line and make it red, and then I'm going to examine it, and as it goes to the left and as it goes to the right, it looks to me like I've got the correct asymptote. And then in letter C, again, the degree of the numerator is the same as the degree of the denominator, and they're already written in standard form, so your horizontal asymptote is going to be this time not 2 over 6, because that's a fraction that can be reduced, but it's going to be y equals 1/3. So now let's draw a couple of graphs. Go ahead and put this equation into Desmos. Remember to type f of x. Remember that when you're entering these into Desmos, you have to put parentheses around the numerator before you type divide. It's pretty much the only way I can get Desmos to make a fraction. This is number 22 in your test review guide, and it's asking you to draw the graph of a rational function. Remember that when you need to make a table of values, which we're going to do in just a minute, you want to start your function equation with f of x. So I'm going to type f of x equals, and then I'm going to put parentheses around the 2x plus 1, then divided by, and then x squared minus x minus 2. So this is how my graph looks. Again, I think I'm going to change this to projector mode for you so you can see it a little bit better. And you have already factored the denominator here, and you see that it's x minus 2 times x plus 1, and so you have vertical asymptotes at x equals negative 1 and x equals positive 2. I'm going to go ahead and draw that in. And I'm going to make them both dashed and red, dashed, and it's already red. Ooh, one of them is bold. There we go. And so it looks like my asymptotes are accurate at negative 1 and positive 2. I want to look at my y-intercept and my x-intercept, and look, they're both negative 1/2. And then I can also make my y-intercept, which I am looking at the equation because the degree of the denominator is greater than the degree of the numerator. The degree of the numerator is 1, the degree of the denominator is 2. I think that my y-intercept is 0. And if I make that red also, you'll see that that also looks fairly accurate. Now, you don't have to put all of the asymptotes into Desmos. I would do that if I wasn't sure about what the asymptote is, or if I computed it algebraically and it doesn't sound quite right. It's just a way of double checking yourself. The other thing to remember, we mentioned this a little while ago, is that your horizontal asymptote, unlike the vertical asymptotes, the graph can cross the horizontal asymptote in the middle. The horizontal asymptote is only about the end behavior, what's happening to the extreme left and what's happening to the extreme right. And so here, although the graph crosses the horizontal asymptote in the middle, it doesn't matter. It only matters about the far left and the far right. The vertical asymptotes can never be crossed by the graph. Now I'm going to go back and make my table of values. So f of x, that's not right. Table of values, go to add item and then table and then change y1 to f of x1. And I got rid of the dot, and I don't know if that's going to impact the problem. Let's see. So I'm going to start at -6. It was good. -5, -4, -3, and I'm going to graph a bunch of these. Now, obviously, it's pretty darn hard to graph -0.27 and then graph -0.32 and get those to be real accurate. And then -0.38. So just kind of find a place at -6 for the -0.2, and you see that these gradually move away from the x-axis, farther away from the x-axis, just slightly farther away from the x-axis, slightly farther away from the x-axis, until at -1 it's undefined. Now, there's only 2 whole number x values in between, but if you, let's say, you wanted to experiment with other points, you could say, well, I'm going to graph -0.5. Oh, look, I'm going to graph -0.25. I'm going to graph +0.25. I'm going to graph +0.75. I'm going to graph +1.5. And give yourself kind of a feel for what the shape of the graph is. It doesn't matter that your table's not in order, and you can enter any point values you want to enter. That also goes for what's the graph doing as you get closer to the asymptote. So the asymptote's at x equals 2, and your first point here is x equals 3. But what if you want points between 2 and 3? Well, just go ahead and type in 2.5, 2.75, just type a bunch of stuff, and it'll kind of give you a feel for the shape of the graph and where to put those points. Let's answer the questions algebraically. Remember that for the x-intercept, you set the numerator equal to 0. So here I'm going to say 2x plus 1 equals 0. And so my x-intercept is x equals -1/2. And my y-intercept, I'm going to remember that I'm looking at just the constant term of the numerator and the constant term of the denominator. So the y-intercept is -1/2 again. And I'm going to graph those 2 points over here. So -1/2 and -1/2. Now, when I factor what can be factored here, I have 2x plus 1 over x minus 2 times x plus 1. So nothing cancels, so there's no holes. And if there is a hole, I want you to kind of draw it. If there were a hole in the graph, I'd kind of want you to draw it like that. But there's no holes for this graph, so don't draw a hole. The vertical asymptotes then are going to be the things in the denominator that would make it 0, and so your vertical asymptotes are going to be found at x equals 2 and x equals -1. And go ahead and draw those in right off the bat. So I'm going to draw my asymptotes. X equals -1 and x equals +2. And it's hard to draw the whole space without zooming in. So I've got -1, oops, and +2. So there's my asymptotes there. And my horizontal asymptote, because the degree of the numerator is 1 and the degree of the denominator is 2, my horizontal asymptote then is automatically going to be y equals 0. So go ahead and draw in the horizontal asymptote. Actually draw it right on top of that x-axis. So I'm going to have to go back and put in my x-intercept. My iPad is slowing down a little bit here, probably because the video is so stinking long. Sorry about that, you guys. And so then I'm going to use the tables in Desmos to graph the points. The -4 is kind of ridiculous because it's 0.3888889. You know, you can't graph that really. So I'm going to go ahead and graph a point at -3, -0.5, and -2, -0.75 is just a little bit lower. And then you see that that graph is going to go toward the asymptote in that direction. So I'm going to go ahead and fill in that part of the graph there. And then in the middle section, the only 2 points I have are the x and y intercepts. And so I'm going to look at the graph in Desmos for the shape, but it basically ends up doing this toward the asymptotes. And then the other points that I can graph 3 and 1.75, which is about there, and I can graph 4 and 0.9, and I can graph 5 and 0.6, but then that gets closer and closer to the asymptote there. So that gives me the general shape of that part of the graph. And so here I'm going toward the asymptote there and up here. And so this first graph should look something like that. And then go ahead and clear out the first equation in Desmos and type in that second equation. It's going to look a little bit different, this graph. So go ahead and do that. And last but not least, number 23, start by typing f of x because we want a table of values. 20x over x squared plus 2. Oh, now that's interesting, isn't it? So let's zoom out just a little bit. That's an odd-shaped graph. Remember that rational functions act irrationally. That was a joke. Haha. So you can see that you have your x and y intercepts are 0, 0. The denominator is not factorable, so there's not going to be anything that cancels, and therefore you won't have any holes. But also, the denominator can't be set equal to 0. Again, just like a previous problem, x squared is always going to be positive, and you're adding to a positive number another positive number. There's no way to make the denominator 0, so there aren't any vertical asymptotes. So this graph won't have a vertical asymptote. And also remember that your horizontal asymptote is about the end behavior. So as the graph goes infinitely left, as the graph goes infinitely right, your end behavior goes towards 0, or the graph goes towards 0. And remember that algebraically, that's the degree of the denominator is bigger than the degree of the numerator, which is smaller. So the degree of the numerator is 1, the degree of the denominator is 2, so therefore you're going to have a horizontal asymptote of 0. The other thing that I would do if I were you in graphing this, let me put this back, is I would not only click on the graph to find the x and y intercepts, but I clearly see a maximum up here, and I clearly see a minimum down there. And although the question on the paper doesn't ask you to find minimums and maximums, it helps you graph that, because now you know exactly how high to go and where. and you know how low to go and where. So where x is 1.4, you can put a point at 7.07 or a little bit past, slightly past 7. And so once you've got those 2 points graphed, now you can add your table and change y1 to f of x1, and then I would graph, I wouldn't graph all the way out to -10. Maybe I would. Let me just not do the points in order. So let me say I'll graph -10, but then I'll skip back into -5, and then go -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, and then +10. And in that case, you can kind of get a feel for the shape of the graph as it's going on the left and on the right toward the horizontal asymptote. Did you notice, wait for it. Did you notice that this is an odd function because it has point symmetry, rotational symmetry about the origin of 180 degrees. So if we were to rotate it, this point would become that point. And if you substituted -x here and -x here, the entire f of x would be negated. Not that you needed to know that. I just think it's cool. And now let's look at the x and y intercepts. The x-intercept is going to be what makes 20x equal to 0, so x equals 0. And the y-intercept is also going to be 0. If the x-intercept is 0, the y-intercept is 0. So I'm just going to put a point there, and you can see by looking at the graph that there's no other x or y-intercepts. Now, the bottom is not factorable. That's not factorable. And so there's no holes and there's no vertical asymptotes because nothing can be substituted into x squared that would make the denominator 0 because you're adding to x squared. And even if you substitute in a negative number, it'll become positive when you square it. So there's nothing that will make the denominator 0. So no vertical asymptotes. The horizontal asymptote, remember, is about the degree, and so the degree of the numerator is 1, the degree of the denominator is 2. If the degree of the denominator is bigger than the degree of the numerator, then your horizontal asymptote is y equals 0. I hope that dropping my pen didn't make a really loud sound in the video, sorry. And so I'm going to go ahead and draw my horizontal asymptote here. And it does say that you have an x-intercept and a y-intercept at 0. Remember that with a horizontal asymptote, the graph can cross in the middle. A horizontal asymptote is only about the end behavior of a function. So now I'm going to grab the other points for this function from the table in Desmos. And you've got this min and this maximum. And I'm going to kind of, just to help myself get an idea of where the graph turns around, I'm going to graph those 2 points. So the minimum happens at -1.5 and a little past -7. So -1.4, -7.1. So -1.4, -7.1. So right about there, and +1.4 and +7.1. So that's going to be right about there. And then the other points that I can graph, I've got -4 and negative, I guess that if I went out all the way to, hang on a second, if I went out all the way to -10, I didn't do this ahead of time, but that would be about -2, -1.9, and then I'm going to just go ahead and go into -5, which is -3.7, and then -4 is -4.4, -3 is -5.4, 2 is negative 6.6. And then it hits that turning point, and at negative 1, it's also negative 6.6. And so it comes back to just about the same place there at negative 1. And then it goes to 0, 0. So the graph kind of on the left does this kind of thing, and keeps getting closer to the horizontal asymptote here on the left. And then it's going to do something similar on the right. So at positive 1, it's positive 6.6. And then positive 2, it's also positive 6.6. Positive 3, 5.4. Positive 4, 4.4, positive 5, 3.7, and again at 10, it's going to be about positive 1.96. And so on the right side of the graph, it's going to come up like this and come down and out like that. So the graph should look like that. And just because you wanted to know, I'm going to give you this little extra piece of advice that has nothing to do with anything other than you recognize this as an odd function, because it has point symmetry about the origin of 180 degrees. And if you were to plug in negative x, 20 times negative x, all over negative x squared plus 2 gives you negative 20x over positive x squared plus 2, which is exactly the opposite. That's negative f of x. And that is odd, proven algebraically and graphically. And you don't need to know any of that for the Unit 7 test. I just thought it was a fun fact. Fun fact. And aren't you glad to be done with this big, huge packet? Sorry the video is so long. Hope it's helpful. Let me know if you have questions.